I know I'm going to like forget this one day. I just know I will. You've plenty of opportunity to ask should you have made time for that. Plenty of time to get those questions done. I mean, there was only, I think, 4 on that, but they take some time. I mean, you can't just expect to sit down the night that it's due and knock them out unless you're just really awesome at this, and then I'm happy for you. But because it's Thursday and it's a holiday weekend and we need to keep moving forward, I'm going to talk about section 4.5 today that has nothing to do with optimization. So maybe it'll be a breath of fresh air. And then we get through that. I don't think it'll take the whole class. We can jump back and talk about optimization if you need to. I'm just happy that I have power, because at 4:30 this morning, a huge storm rolled through the Wilkesboro and it shook the whole house with thunder. So there wasn't internet. The internet was out for a couple hours. The power never went out, but the internet and the cable were gone. So I'm just happy to have this. 10 on the, hey, I can. And Riley, I could even forward you one that I sent to somebody else about question 10. Question 10 is on the homework is that the cone question? I think. Cone. No, it's a cylinder. It's almost like one of the cylinder questions that we had, but there's no cost attached to it. So you have a volume and you have a surface area. I think that's what that one is, because I helped somebody with it on email yesterday. But yeah, at the end, if we get through some section 4.5 stuff, we'll come back to that. Do you see they're over there on the counter? Okay. All right. So how many, if you know how to raise your hand on here, on the participant list, I think you have the ability to raise hand, or I don't even know what kind of reactions. You can give a thumbs up or a clap, whatever. If I say L'Hopital's rule, does that resonate with anyone? No. Oh yeah, you have yes or no on here too. Oh, there's a yes. You can click yes. This is so different. Sky says yes. Everybody else is either not listening or doing something else or doesn't know what I said. Okay, Brian says no. Anybody else? L'Hopital rule? If I say L'Hopital? No, no. I mean, if you've never had calculus before, you're not going to. Unless you've looked ahead, you wouldn't have. And so for the rest of you, I don't know what you're doing, but we're going to talk about L'Hopital's rule today. Boy, eat your food. Okay, so let me go and switch to iPad and start. I did already post some notes for this. Should you, oh no. Hey, come here and answer this. I don't know. Had the power company come out today too, because my box is making a weird static noise. Yay. So just let my 8-year-old answer the phone. What are they saying? Oh, just hang up. It's okay. You suck. You don't have to say that. Gosh, kid. I love you though. All right. Oh, not that. Come back, Zoom. Okay, section 4.5. So section 4.5, if you can see this, looks at something called indeterminate. That just looks wrong. Indeterminate. Is that spelled right? Indeterminate. Yep. Indeterminate. Okay, we'll just say that's right. Indeterminate forms. And then it's kind of spelled like the word hospital, but there's no S. Let me let Aaron into the class. And it has this little, whatever that thing is called. We call it a hat in statistics. I don't know what it's called in the real world of phonetics, but it's called L'Hopital's rule. So this is going to be a section about limits. And we did limits in chapter 1, where we could plug things in and we had rules and we could graph and we could look at end behavior. But L'Hopital's rule is going to help us with things that are of something called indeterminate forms. I swear that looks wrong, but we're going to roll with it. And it has nothing to do with optimization, but it is in the chapter 4, which is the application of the derivative. And we are going to use the derivative in this L'Hopital's rule. Okay, so to begin with, I would like to have you go back to a simpler time when we did the limit as x goes to a number Sometimes we did x goes to infinity. It's just limit as x went to something. And we had a fraction, like a rational function. It was the limit of a quotient. And the section was 1.2 when we did these before. And in fact, we did infinite limits in section 1.5. Maybe you remember that, like when the x's got really large or when the x's got negatively large. So go back to that if you can. Like I said, most people really love this section because it's easier compared to the optimization that we have been doing. But the limit, there was a limit rule, which we sort of touched on, but not exactly, that said if you have the limit of a quotient, then you can evaluate it as a top function, and you could evaluate it as a bottom function. And if that gave you a limit, then you were fine. Like if we did, I'm trying to think of one that we would have done. Like limit as x goes, I think we did infinity, like 1 over x, right? Because if you did 1 over a really, really large number, we talked about how that went to 0, right? You remember doing those? I mean, limits are just function value, function behavior when x behaves like it's supposed to. So we did talk about those, but we had some that looked like limit as x goes to 2. So let me see, but follow along with my notes here. Do you remember this question? Like x squared minus 4 over x minus 2. And if you could plug it in, you were told to just plug it in if you could, right? Like if we had the limit as x goes to 3 of 2x plus 1, you could just literally plug 3 in and get 7. It's just a function value. And if you could plug it in, you plug it in. Otherwise, you had to do like some algebraic manipulation to make it where you could evaluate it. Because 2 is a problem here. When we try to do, when we try to split this as x goes to 2 for x squared minus 4 and x minus 2, you end up, like if you just plug 2 in, you end up getting 0 over 0, and we couldn't do that. Like that's not, some of you, I don't really think it like sunk in at the time. What do you need? Oh, I have no idea. Maybe you took it to a bedroom. Who knows? They've been everywhere today. If you plugged it in and got 0 over 0, there were several of you that incorrectly wrote like does not exist, and that was wrong because the limit did exist. You just had to sort of like algebraically manipulate it. So we couldn't use if it was in this form. And so what we had to do is, that's not a W. We did some algebraic, everybody's favorite algebraic manipulation of the question, where we said x squared minus 4 is really x minus 2, x plus 2. And then the x minus 2 canceled because it was like a line with a hole in it. So we were really evaluating the limit of x plus 2. And if you plug that in, then you got a good number, and it was 4. Do you guys remember doing this? I mean, I know it's been like a couple months and spring break times 2, and then coronavirus, don't leave your house, don't touch anybody, or talk 6 feet, whatever. Do you guys remember doing that? Because we did do it. It was back in chapter 1. I see as a no. You guys don't remember doing this. Okay, well, we did do it. I swear to you. But we had to do, like, you couldn't just directly plug the number in because it caused the zeros. So we had to do some kind of algebra, or I just said graph it. Okay, so what happens, we even had ones like, let me get another piece of paper here. Do you remember this trig derivative, sine x over x? It made this funky little graph where it went whoop, and at 0 it was 1. And it was one of those, you can't plug 0 in. All right, if you try to do sine 0 over 0, you get 0 over 0, and we can't have this. So I just said memorize that it's 1, graph it, you can see. Maybe you remember that one. We also had ones where we looked at like x went to infinity, and then we had rational functions like 3x minus 2, x squared plus 4, right? So if you try to look at them from, like if you do the limit definition where it says you can split them, then you know, if you try to do the 3x minus 2, or if you try to do the x squared plus 4, like if you try to evaluate the limit separately, 3x minus 2 is an infinite limit, x squared plus 4 is an infinite limit. So we really couldn't like evaluate that. And so I don't know if you remember, but just to refresh your memory, it's a good exam review. If it was in behavior on a rational function, we pulled the leading terms. And if the bottom was higher, we said that it went to 0. And if the top was higher, it went to one of the infinities. And if they were the same, I don't know if y'all, again, I know it's back in a simpler time, but if it was like 3x over 2x, then the ends of it went to 3/2. Maybe it was just called in behavior of a rational function, or you could graph it. But that's what we did on that section when we did the infinite limits. I'm pretty sure it was section 1.5. 1.5 was the infinite limit section. Okay, so those are all, I don't want to say tricks, but they're using properties of the function that you've been given, or possibly, like I said, memorize the sine x over x is 1 when x goes to 0, or graph it. So what this section presents to you is a way to use derivatives as an application of the derivative to do this in an easier manner, okay? So what this is good for, let me go to this other page. I don't need that. Oh, so these things that I wrote here, this 0 over 0, infinity over infinity, over here, when we put in the limit and we get 0 over 0, those are called 0 over 0 and infinity over infinity as like an expression. These are referred to as indeterminate forms. I'm having a really hard time with this word today. Indeterminate, just looks wrong. Indeterminate forms. And there are others, but they're just like, you can't determine any information from them because you can't divide by 0. Infinity over infinity is not something that you can do. You can't, indeterminate, you cannot determine an answer from the form that it's in. There are others that are presented in your textbook, which is why I didn't give you a guided learning on this, because it uses them and we're not talking about them. Like if you have an infinite value, subtract an infinite value. Another one is if you raise 0 to the infinity power, that's not a thing. If you raise 1 to an infinite power, and what's the other one? Oh, infinity to a 0. All of those are considered indeterminate forms in the world of calculus, but we are going to focus on those two, and that's all. So your homework isn't picked to only choose those two. So those are the ones that we're going to do. And to begin with, you are asked simple questions of identifying what kind of form it is. I have a question. People have microphones on and you breathe, I hear it. So I'm just making sure nobody has a question. No? Okay. So if I gave you an example like cosine of 3x minus 1 over 2x at the x value of 0. So like imagine this was a limit as x goes to 0. Would this be one of those indeterminate forms? And all you're doing is you just plug in 0. Just plug in x equals 0 and see if you get 0 over 0 or infinity over infinity. Usually when you plug in zeros, they give you zeros. But like I say, just take 0 and plug it in, like cosine of 3 times 0 minus 1 over 2 times 0. That'd be what? Cosine of 0. What's cosine of 0? Unit circle. 1. 1 minus 1. Don't you get 0 over 0 for this? Yes? No? Are you with me? The 19 of you that showed up today? Out of 36? Yes? Okay. So this one is a 0 over 0 form, and it's just like I think Wiley, no, not Wiley, you guys use Sapling. I think Sapling has a multiple choice for you to choose which one you get, but this is a function that would give you 0 over 0 form. Another one, again, just to give you an example, like if you had x squared over e to the x, and you were looking to evaluate that at infinity, like an infinite value, what would happen if you tried to take an infinite number and square it? What kind of number would you get? Pretend we're sitting in class and you're participating with me today. Let's pretend. You all are young enough to have active imaginations. You would get an infinite number. Yes, thank you, Sarah. If you tried to do e to an infinite number, like e is exponential growth and it grows the bigger the input gets. So you would get an infinite number again, and this would be an infinity over infinity form. So you're just taking functions where it tells you to look, and you're just identifying if it's one of those two indeterminate forms. I mean, I don't know. No, I don't think I need to do any more of those. So your ability to acknowledge whether or not this is an indeterminate form is crucial to use L'Hopital's rule, because if you don't have a function of that form, you can't use it. Okay? So let's talk about L'Hopital's rule. I'm sure that little thing has a name, but I don't know what it is. So L'Hopital's rule is a rule that's going to give us the ability to evaluate a limit of indeterminate form. Like that's what this rule is going to do. And it's going to use the concept of a derivative. Okay, so, but it has to be a limit, and it has to be either 0 over 0 or infinity over infinity. Those are the only ones that we're going to focus on for this section of work. Okay, let's see. 1 over 0 is undefined, so you cannot have that. It's only indeterminate if it's 0 over 0 or infinity over infinity. But 1 over 0 is undefined. 0 over 1 is just 0. If you get the number infinity, it's still infinity. But the moment you start putting infinity over infinity or 0 over 0, those are considered indeterminate. So 1 over 0 is not. It's just undefined. Okay. So if we have, here is your L'Hopital's rule. So you have to have f and g, and they have to be differentiable. So they have to have a derivative. They're differentiable on some interval I. This is textbook definition, by the way. And f and g are in a rational function where you get 0 over 0 or infinity over infinity as an indeterminate form. Then what you can do is basically, because I'm going to write the textbook thing, but here's the big picture. You can take the derivative of the top and the derivative of the bottom, not a quotient rule. So some of you tried to do this when we did quotient derivatives to begin with. You do the derivative of the top function and the derivative of the bottom function, and if that has a limit, then it's the same as the limit of the function. So let me show you that in like definition words. It says if the limit as x approaches c, but it also works as x approaches c from the right, or x approaches c from the left, or as x approaches one of the, it works for any of those limit definitions. If you do the top derivative over the bottom, like if you take the derivative and then evaluate the limit and you get a number, like this is an actual real number derivative, you know, like 2 or 1/4, or it might be infinity, because if it's like x squared's limit could be infinity if you were looking at infinity. As long as you don't get an indeterminate form, some non-indeterminate, I'm not writing that word out again, that's just a long word. Some like if you get an actual real number there when you do the derivative, then that's the derivative of the original function. So then the limit as x goes to c of the original is the same answer as up here. I'm gonna show you an example because this is textbook mess. But that's what L'Hopital's rule says. If f and g are differentiable, you have them in a fraction ratio rational function where you get an indeterminate form, then you can do the derivative. So we're applying the derivative. It's not a quotient rule. If you do the derivative of the top and the derivative of the bottom, and that's a limit you can use, then that limit is the same for the original function. So I'm going to show you this for the one that we did, the first one. So the limit as x approaches 2 of x squared minus 4 over, I don't remember what it was, x minus 2. We did this one at the beginning, right? You couldn't plug 2 in. If you tried to plug 2 in, you got 0 over 0 form. So we'll use L'Hopital's. I'm also not writing that word out again. So if we use L'Hopital's rule, what that says is to take the derivative of the top. What's the derivative of x squared minus 4? Like really simple, x squared minus 4. What's that derivative? Maybe somebody's chatting. No, are you guys alive today? 2x. I got 4 of you saying 2x. Good. So instead of x squared minus 4, I'm going to replace that with a 2x on the top. It's just the derivative. Like the derivative of x squared minus 4 is 2x. What's the derivative of x minus 2? 1. Can I evaluate this limit at x equals 2? Can I plug 2 in? What do I get if I plug 2 into that function? 4. Isn't that what we got before when we factored and did all that and then plugged it back in? Much easier than factoring, I promise. So all we did was take the derivative. It's pretty simple, okay? So it has to be indeterminate form, and if it is, you do the derivative of the top, you do the derivative of the bottom. If you can apply the limit, do it, and that's the same answer. Since this is a limit, then we can say that the limit as x goes to 2 of the original function is also 4, which it was because that's what we did for the first example. Okay, let's do another one. How about, we'll do the x, no, let's do the cosine one. So the limit as x goes to 0 of sine x over x. So if you try to do the plug-in, like evaluate the limit, plug in the function, if you do sine of 0, try sine of 0 over, you get 0 over 0 form. And if you have that, let's use L'Hopital's rule. And I'm not writing that word out, so I don't feel like writing that 0. So if you apply L'Hopital's rule, what is the derivative of sine x? I'll write it out one more time. So the derivative of sine is cosine, right? Is that what a few of you keep? I should leave the chat up. Okay, yeah, so the limit of sine, so the top would just be cosine. What is the derivative of x? Okay, can you evaluate it now? So try to evaluate at x equals 0. If you do cosine of 0 over 1, what do you get? Cosine of 0, unit circle, 1 over 1, you get 1, right? So this is a real number, and because we applied L'Hopital's rule, got a function that we could evaluate. Again, it's not a quotient rule. It's just straight derivative of the top, straight derivative of the bottom. If that gives you a function where you can evaluate it and it gives you a real number answer, then that is the limit of the original function. And that's the limit that I had you memorize, but I couldn't show you this until we talk about L'Hopital's rule. So if that's true, then the limit as x approaches 0 of sine x over x is 1 also. It's a very easy rule. in the grand scheme of everything that we've been doing with the applications of the derivative. Let me show you this other one. How about the limit of x squared over e to the x as x goes to infinity? Okay, so for this one, if you try to, I know you can't really like plug in infinity, but you could evaluate it when x, you could do the limit. If you try to split this up and evaluate the limit of x squared and e to the x separately, if you do e to the, or x squared is a parabola. When the x's get really large and you square them, that's an infinite limit. If you take e to the x, that's exponential growth. And as that power gets bigger, the function gets bigger. So this one gives us an infinity over infinity form. So because that's one of the indeterminate forms that we'll have in this section, we can use L'Hopital's rule. But you can't, again, you can't use the rule unless it's an indeterminate form. You can't just start using L'Hopital's rule on limit. I'm just going to do this. It has to be one of these forms before you can do it. So if we apply L'Hopital's rule, then what we're looking at is the limit as x goes to infinity. Okay, so what's the derivative of x squared? Am I recording this? Okay, good. 2x. So the numerator becomes 2x. How about derivative of e to the x? E to the x, okay. Now try. What happens if you try to evaluate as x goes to infinity now? What do you get? Like if you split them, like if you try to do the limit of 2x and you try to do the limit of e to the x, what happens again? I say again because like 2x is a linear function. As x gets bigger, it's just going to get bigger, and e to the x keeps going. We still have an indeterminate form. So guess what we can do again? Do it again. Do the L'Hopital rule again. And you may have functions where you have to do it a few times, because as long as you keep getting an indeterminate form, you can still do L'Hopital's rule. So we still have indeterminate form. We'll do L'Hopital's rule again. So this would be the limit as x goes to infinity. Okay, now what's the derivative of 2x? 2. Thank you, Elliot. And e to the x derivative is e to the x again. Now let's look at that function. Okay, you've got a number over e to the x. If you try to evaluate that limit at infinity, talk to me about what happens to that function when x gets really large. You have the number 2 over e to a really large number. What's going to happen to that function? Good, Brian. Brian says it goes to 0. We've had functions like that. It's not an indeterminate form. It is 2 over an infinitely large number. And if you have, see, if we evaluate again as, I swear that says as x gets really large, x gets large, then what we have is 2 over a really large number, and that thing goes to 0. So we have a function, 2 over e to the x, where we applied L'Hopital's rule twice. We evaluated the limit. We didn't get an indeterminate form, but we got a limit value of 0. So because this is a real number, then that is the limit of the original question. So this is a real number limit. So that means the limit as x goes to infinity of x squared over e to the x also goes to 0. Does this make sense? Is this better than boxes and fences and maximizing wire stuff? It's a pretty easy section compared to things that are in chapter 4. I mean, yeah, chapter 4. Okay, but just know you can't use L'Hopital's rule if it's not indeterminate, and you may have to do it a few times. And it does require that you remember derivatives. I'm talking natural log derivatives, power rule. Let's try to see what other, I had some more examples. Oh, there's a good one. Do I have room? Nope. Here's a trig one. So let's say we had the limit as x goes to 0 of tangent over 6x. If you try to evaluate, again, whenever you do limits, the number one thing you should do, because limit's just a function value, function behavior when x goes to 0, just plug it in. If you can plug it in and you get a number, go with it. If you plug it in and you get the weirdness, evaluate it. If I try to plug in 0, if we try to just straight up evaluate this at x equals 0, we get tangent of 0 over 6 times 0. Do you guys know what the tangent of 0 is? Tangent is y over x on the unit circle at 0 degrees or 0 radians, whatever. If you try to do tangent, it's 0 over 1, which is 0. So you actually get a 0 over 0 form for this function. So this function, you are allowed to apply L'Hopital's rule. So, and other than just graphing it, I mean, like I said, you're welcome to graph it. So I found this out yesterday and it like made my day because I was trying to grade your all's quizzes and have a split screen, and I'm not even kidding, it made my day. I'm such just like electronic nerd last night. It made my day. If you try to, let me go to radians. If you just graph it like 10x, not that though, and then divide it by 6x, and you try to look as x goes, I mean, this is what you probably did in chapter 1, is you just graph it and looked where it went at 0. And if I try to go to 0, that is, I won't let me pick it, I won't let me click on it. It's decimal. Oh, it says undefined because it can't be 0, right? So other than just trying to guesstimate what that number would be, like 0.1 something, 1617, this is not really something that you could give exact. You could probably make a pretty good guess, but you can't pull it nicely. It has a limit. It's not defined at 0, but it has a limit because the functions go, like it's from the left and the right, it goes to the same place. But in order to find out exactly what it is, I'm telling you, split screen, it made my semester. Because you get this indeterminate form, we can do L'Hopital's rule. So if we get indeterminate form and we apply L'Hopital's rule, then talk to me about what those pieces would be. Like the bottom is 6, you should get that. But what's the derivative of tangent? This is back from chapter 2. So that's the secant derivative, Brian. But you're in the right ballpark. Yep, Brianna says it's secant squared. So the derivative of tangent, let me put this here. The derivative of tangent is secant squared. That's going to go here. Okay, now try to plug it in. Can you plug in 0? Try to evaluate it. Try to, you're not going to get indeterminate because it's 6 on the bottom. So let's hope the top is a number. If it's 0 on top, 0 over 6 is 0. That's a real number. That's your limit. So if we try to evaluate it at x equals 0, all right, so what is secant squared of 0 is the same as secant, that's theta, of 0 squared. What is secant? Do you remember what secant is? Secant is the reciprocal of cosine. And if you don't remember what secant of 0 is, pop your calculator. Well, I don't really know that it would matter. Degree or radian. We've worked in radians this whole course. You can type it if you want to. But yeah, secant is just the reciprocal of cosine. And cosine of 0 is 1. 1 over 1 is 1. 1 squared is 1. So secant squared of 0 is 1. And you get the number 1 over 6. And 1 over 6 is 16666. That's what it was trying to approach on the graph when we pulled it up before. But the exact answer is 1/6. And you really can't like get that easily without using L'Hopital's rule. So what L'Hopital's rule is doing is it's allowing you a method to use a derivative of those function pieces to come up with a function that you can evaluate the limit really easily compared to what you could have done. Does this rule make sense? For most people, should I look and see, are you doing the yes, no, hand clap? I'm gonna clear all this and let you do it again. Because some people's were up there from before. Yes, this rule makes sense. No, this rule doesn't make sense. Paying attention in the world of, I got one yes. Thanks, Haley. 2 yeses. It's really not a hard rule, I promise. Okay, and I don't know if I have any other like weird ones. We might do one that has a natural log just to, and maybe that one. Okay, so maybe 2 more, and then you see if you have other questions. What if you did the limit, where did that go? Natural log of x over x. As x goes to infinity of natural log of x over x. Okay. So again, if you were trying to evaluate this limit, I know you could graph it. You're welcome to if that's what you want to do. But you're going to be expected to show this rule from this section. If you were doing this and you separated it and you tried to evaluate the natural log and you tried to evaluate the x, you are going to get an infinite over infinity form for this one. Okay. So this is an indeterminate form if you try to just evaluate it at really large numbers. So because we get that, we'll apply L'Hopital's rule. So here's the question. What is the derivative of natural log of x? Because I know you can get derivative of x is 1. What is the derivative of natural log? This is a chapter 2 thing, maybe 3. 2 or 3. 1 over x, good. So if I do 1 over x here, that's like 1 over x over 1, which is really just 1 over x, right? If we got rid of the 1. Can you evaluate that limit? Like, can you tell me what that limit would be, 1 over x, if x got infinitely large? We've done these. So if you have 1 over super large number, that fraction as a whole goes to 0. Good, Haley. So because we applied L'Hopital's rule, got a function where we could evaluate the limit, this is a real number. So that means the limit as x goes to infinity of natural log of x over x is 0 also. Okay? I got one more, and then we'll see if you have questions. What about, trying to see if I can fit it on this page in case you're still writing. E to the x over x as x goes to infinity. Infinity. Is that an indeterminate form? Yes. Brianna says yes. I can't really see if you guys are like. I miss your face. Okay, so yes, it is. If you do e to a really large number, you get infinity. If you do x, I mean, it is, you get infinite over infinite form. So we'll use L'Hopital's rule. So if I do that, derivative of e to the x is just e to the x. The derivative of x is 1. So what you're really looking at is the limit as x goes to infinity of e to the x. Talk to me about what that limit does. Like, that's exponential growth function, and what happens when x gets really huge? It goes to infinity. Anybody else have a thought? Never stops going. E shows up to the party, it never stops. That's what I used to say in pre-calculus. Completely inappropriate reference to drugs, but yeah. It doesn't approach 0 if it's growing. If it was decaying, it would be 0. But yeah, this one is actually called an infinite limit. We had them in section 1.5. So it's not an indeterminate infinite over infinity, so we don't have to do L'Hopital's rule. This is an allowable limit answer. So again, this is allowed to be an infinite limit. It just means it grows up and it gets huge and it gets, you know, it just goes to infinity. And you're allowed to have that. It's just if you get that infinity over infinity form, you have to do L'Hopital's rule again. You're allowed to get 0 for a limit. You're allowed to have the infinity as a limit. So that's your answer. And since we got that answer, this is allowed, then we can say the limit as x goes to infinity of our original function is infinity also. Like I said, you could probably graph it, but you will be required in a section to show the use of L'Hopital's form to get the limit answer. So does anybody have L'Hopital rule questions? 143. Now would be a good time. The homework is there. The homework is up. There's no guided learning because the guided learning did all of the other forms and I wasn't trying to, these are the only two we're worrying about for this class. Anybody have a L'Hopital rule question? No? No? Tori says no. Okay. Well, and nobody else is, I swear. Maybe I should just make you turn your videos on. Nope. So yeah, we can look at that one, Tori. So that's, I mean, that's all that there is to section 4.5 that we're gonna do. There's the only other thing that's in chapter 4 that we're gonna cover will be after your next test, because this is gonna be stopping point for test. 4.8 introduces you to something called an antiderivative, and an antiderivative is the opposite of a derivative. So it would be like if I gave you secant squared and said, what's the antiderivative? You would say tangent because it's the function whose derivative was secant squared. It's just a backwards derivative. It's going to lead us into chapter 5 where we do integrals, but section 4.8 is antiderivatives, and we're not going to, we'll do it next week. But you're going to have, it won't be this weekend because it's Easter weekend, Sophia. So if anything, we might review on Monday and the test will be due by Tuesday, maybe. But you are going to have an exam due sometime early next week. I'm not going to make anything due over Easter weekend, a holiday. So I'm not supposed to. Okay. But I can post some review stuff if you want to look at it and try it. Plus you have homework to do. So if I go back to, Tori, I'll be honest, I don't know which one you're referencing that we started yesterday. You know which one it was? I got a lot of pages open. We could do this math story that my 6-year-old did. You'd rather do that? Oh gosh, the wire question. Let's see. Go back here. This one? I think it's that one. Yeah. And again, this one is written out in its entirety in a document just like this in As You Learn. And yesterday, I don't remember when, evening, afternoon, sometime yesterday after class, I posted like 3 or 4 documents of examples worked out like we had been doing. And I think I even posted one that we did on the cone that we did for class lecture yesterday. So to talk about this one more, you do get, let me see. Let me erase this, clean up some and all the little squiggle things. So you have to take the derivative of this. So to clean it up some, and I don't know if it would help you, what kind of time do we have? Okay, 1:46. Here's what I'm gonna do, Tori. I'm gonna go to this one. It's not that one. Is it this one? Oh, that's the one we were just in. Got way too many things open on here. Thought I had it written out, but I must not have it on this one. It must be in a different one. Okay, it's okay. I can write it. So this cleanup sum that it's referring to would look something along the lines of this. If I square these two quantities, I get 35 minus x squared, and I get 4 pi squared, and then I get x squared over 16. Okay. And this was a circle square question. I think it shows up on your homework set for this one. And I think it shows up on a take home. quiz test things. So you need to know how to do them. They show up. So simplifying it will sort of cancel out some pi's. And the 4 pi that's there, it's kind of like a coefficient on a quantity. And the x squared over 16 is like a coefficient. So writing it like that makes the derivative a whole lot easier to take. And I don't have any more places to write, so I'm going to have to copy and paste it. So I might be able to come over here to the side. So the derivative of this, 1 over 4 pi is a number. It's a number times a quantity with a square. So we can do power rule chain. And then the 1 over 16th x squared power rule. It's pretty easy on that one. So the first part, we'll do a 1 over 4 pi times a 2, a 35 minus x, and then a -1 chain. And then it'll be 1 over 16, bring down the 2 and subtract 1 from the power. And you can't see that because my chat's in the way. So this would look like 2 into 4, that's -35 minus x plus 1/8 of an x. Like you don't have to do anything more to that. This is actually a decimal answer. So you don't have to like just stop there. In fact, I guess if you really wanted to, you could have stopped here when we first did it, but you have to take the derivative. And you also have to, well, actually you can't stop because you have to figure out where it equals 0. Welcome back to algebra. I had this worked out somewhere. I'm about to go find it because I think we're almost out of time. One moment. 11:10, chapter 4. Watch me not be able to find it because I'm trying to find it for class right now. Is it in this one? There it is. So you have to be able to take it. Oh, I think I set this one up differently. Yeah, I did set this one up differently. Crap. Okay. Basically, you can, there's a lot of algebra to this, and you get an x value, and it's a single number, and it's a decimal, and it doesn't have to be exact. And whatever you get for x will be the amount for the square, and you take it away from 35, and you'll get the amount for the circle. But this is going to require that you be able to solve this for x. So if you wanted to graph it to solve and see where its 0 was, you could do that. Otherwise, it doesn't have to be exact. You need a common denominator. Your denominator here would be 8 pi. So you can make a common denominator, set the top equal to 0, and you get some kind of decimal. I forget what it is on this one. Like 19.603 is what I think you get for the critical number on this. So again, this is algebra from this point forward. So if you want to try it, it's 19.603 that you get for the square piece. And then the remainder is for the circle. And with respect to the endpoints, you'll just have to take the original function at 0 and the original function at 35 and the original function here, like a at 0, a at 35, and a at 19.603, and see whichever scenario. This is the absolute stuff, absolute minimum max from back in one of the first sections. And one of those will give you maximum area, and one of them will give you a minimum area. Okay. But I'm going to stop to where if you want to keep staying, I'll hang on Zoom. But I'll stop for now on this one just because it's 1:51. And like I said, these are posted. How to do these are posted. I think when I did this one on the online one, I think I made x the circle and 35 minus x the square. I can't swear it'll make for an easier derivative. I think they're pretty comparable in their steps. But you still get the same answers. But this is the first, and I really feel like it's one of the only ones that show up in your homework where you're asked for both a minimum and a maximum, and you have to be able to consider that it could be none of one and all of the other. Okay, so if you want, we can hang out for a little bit longer. Yeah, I mean, if anything, there's one online on the homework for this. And then I think they may show up somewhere in some take home for test. But yeah, we can look at it. You can let me know. Okay. Anybody else have questions? I lost a few people. What happened? They're like, I'm out. I'm done. I don't want to talk about this anymore. I feel your pain. No other questions? You're good? I think the math lab is open 4 to 7 again online through Zoom, and the online is 8 to 11 p.m., but you're welcome to email with me. I feel like I'm going to lose power. I think he's here. I think I hear his drill taking off. He's about to cut power here for a little bit. But if you want me to hop back on later or after dinner or after, I mean, just let me know. I'll try to log back on with you tomorrow, midday through afternoon. I'm available. You let me know what you might need help on. But otherwise, have a good Easter weekend. Hide some eggs, eat some food, but don't go around people unless you're 6 feet apart. Okay, I'll see you guys Monday.